Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at differential equations. So differential equations are where you have an equation that has a derivative term in it. And we're going to look at a couple of different types. This is called a first order differential equation because the derivative is the first derivative. That is, there are no second, third, fourth, or whatever derivatives. Now, this first order differential equation is separable because we can get all the x's to one side and all the y's to the other side. So if you can do that, you do that because it makes it really easy to solve. You just integrate both sides. So what I'm going to do here is I'm just going to times each side by dx. So I get 3x squared y dx. Now what I can do is now divide each side by y. So in performing those two simple steps, you can see everything with an x is on one side, everything with a y is on the other. So what I can do is simply integrate each side. So here I'm integrating with respect to y. So the integral of 1 over y is going to be natural log of the absolute value of y. And here I'm going to integrate with respect to x. So I get x cubed. Now you have to add a constant on one of the sides. It doesn't matter which here because these were indefinite integrals. So to solve this, I want y as a function of x. The way we undo natural log is we raise e to the power of both sides. I simply get y is equal to e to the power of x cubed plus some constant. So any function of this form, no matter what the constant, it will satisfy this differential equation. All right, let's look at a different type of first order equation. So we're going to solve equations of this form by using an integrating factor. So this is where you have derivative plus p is some function of x times y equals another function of x. Note p and q only depend on x. They're only functions of x, not y. When you have a differential equation of this form, you multiply both sides by what's called an integrating factor. That's e to the power of the integral of p with respect to x. So this integrating factor just makes things a lot simpler. So let's look at this example here. We're going to solve this differential equation. The first step is to find the integrating factor. To do that, we need to locate p. So here we say p times y, so p will be everything that's not the y. So this is my p. So the integrating factor, which I'll call I, is e to the integral of p. So the integral of negative 4 over x with respect to x. So note that the integral of negative 4 on x is negative 4 ln of x. But wait a minute, we can simplify this. We can simply move the power over here using our log laws. It's e to the power of ln x to the negative 4. And hopefully you realize e to the power of natural log of something, they just cancel out. Our integrating factor here is just the function x to the power of negative 4. So what I'm going to do now is multiply each side of the equation by x to the power of negative 4. So now what we can do, it turns out we can basically ignore this part here, and we'll go through why that is in class. What we do is just look at this part, we integrate this part, and we integrate this part, but this time we're integrating both with respect to x. So to make this a little easier on ourselves, we might write negative 4 on x to the power of 5 as negative 4x to the negative 5y. What we're doing here is we're integrating both sides, but both with respect to x. So on this side, I want to integrate with respect to x. So I'm treating y as a constant. So I'm going to leave the negative 4y alone for now. Now with the x's, I increase the power by 1, divide by the new power. Of course, in this case, they cancel out. And on the other side, I increase the power of x by 1, and divide by the new power. But I need to add a constant on one side because these were indefinite integrals. So now I just want to get y by itself, so that y is a function of x. So I'm simply going to multiply both sides of the equation by x to the power of positive 4. So in doing that, I get y on the left-hand side, and on the right-hand side, x to the power of negative 2 times x to the power of 4 is just x squared. So I get minus x squared on 2, but I also have to multiply the constant by x to the power of 4. So any function of this form will satisfy this differential equation. Now let's look at some second-order differential equations. So an equation like this is a second-order differential equation because it has second derivatives in there. So we're looking at second-order differential equations with constant coefficients. So this is how you do it. Basically, you take those coefficients and you solve for r the quadratic a, r squared plus br plus c equals 0. You can solve this using the quadratic formula, factorization, whatever. But it turns out there are 3 cases depending on the solutions you get from this equation. So if there are 2 distinct real solutions, so these two have to be different numbers, then your solution looks like this. If there's only one real solution, like a double root, your solution looks like this, and it gets a bit more complicated if there are 2 complex roots. So if there are complex roots, you have to decompose into the real and complex part, and your solution looks like this. So let's look at one example of each. So we're going to solve this differential equation here. It's second order because of the double derivative here, and it also has constant coefficients. Now what we do first is solve the auxiliary equation. It's going to be the quadratic r squared plus something times r plus something equals 0. The numbers that go here are the coefficients 1, negative 6, and 8. So we're going to start by solving this quadratic here. So it can be easily factorized. The 2 numbers that multiply to 8 and add to negative 6 are negative 2 and negative 4. So the 2 roots of this equation, the 2 solutions are 2 and 4. We have distinct real solutions. So this is like case 1 on the previous slide. So in this case, the solution is simply going to be y equals a. So a is just some constant, e to the power of 2x plus some other constant, e to the power of 4x. So when you have 2 distinct solutions, those solutions go here as the coefficient of x. We can easily differentiate this to show that it is a solution. All right, let's look at another example. So we're now going to solve this second order differential equation with constant coefficients. So our first step is to solve the auxiliary equation. It's r squared plus 4r plus 4 equals 0. Once again, the coefficients of this auxiliary quadratic came from these numbers here. So if I solve this, I end up getting r plus 2 squared equals 0, r equals negative 2. This one has only one distinct real solution. So in that case, the solution here is y equals, again, some constant. So it's e to the negative 2x. It was negative 2 because that was the solution. And the other part of this is b, some constant again, but this time it's x, e to the solution times x. So that's our solution, and we're done. All right, let's look at the third type, which is a bit more complex. So again, we have a second order differential equation with constant coefficients. Our first step is to solve the auxiliary quadratic equation. So here it'll be r squared plus 2r plus 17 equals 0. So we're going to have a hard time factorizing this. Let's instead use the quadratic formula. So here the discriminant is b squared, so 2 squared, minus 4 times a times c. Turns out the discriminant here is negative 64. That's why it doesn't have any real solutions. But we can come up with the complex solutions from the quadratic equation. So they will be x equals minus b plus or minus the square root of the discriminant over 2 times a. So note here, square root of negative 64 is not real, but it's actually just root 64 times I being the square root of minus 1, so it's actually 8i. So the complex solutions here are negative 4 plus or minus 8i over 2. Let's just divide everything by 2 to make it a bit easy. It's negative 2 plus or minus 4i. So on the original slide, we called this real part of the solution k, and the coefficient of I is omega. So what will be our solution to this differential equation? Well, it's going to be y equals, again, we're just going to call it a some constant, e to the power of k, so k is the real part of our solution, times x, and then it's cos omega, so that's the imaginary part of our solution, we just take the positive there. And then it's plus b, e, again to the power of the real part of our solutions of the auxiliary quadratic, this time times sine of the imaginary part of our solution times omega. That is our solution where a and b are constants, and we're done. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.